Hey guys, this is Unit 6 Thermodynamics. We have 6.8 Enthalpy of Formation on this video. Go ahead and pause the video and write down this learning objective now. You have that equation at the bottom. The little E looking symbol there is meaning the sum of. So that is the sigma and it means the sum of. All right, so there are 4 methods. We've seen this on the last video that you just watched. There are 4 methods for finding delta H. We have already done numbers 1 and 2. On this video, we are going to look at this one right here, calculating it using the enthalpies of formation. So what we did in the last video was use average bond enthalpies. This is not very accurate at all. Okay, so this gives us a very inaccurate number to calculate the change in enthalpy, but when we use the enthalpies of formation, this one's a little bit better. And then in 6.9, which is the last part of this unit, we will do Hess's law. All right, so what we have here is a standard enthalpy of formation. So this is indicating how much heat would be lost or gained during the formation of 1 mole of a compound from the most common form of its element in its standard state. So what we're saying is that it has to be at 25 degrees Celsius and 1 atmosphere. And we're talking about the enthalpy of formation, meaning about how much energy is going, what's the change of energy when that particular thing is formed. This is like really ideal situation, so this isn't something that we're really going to do in the lab. An example here would be methanol. When we look at all this, we're looking at these in their standard form. So for example, carbon here in its standard form would be a solid. And then when we have hydrogen as a gas, you notice that hydrogen as a gas is in its diatomic form. Same thing with oxygen as a gas in its diatomic form. So if I were to write water in its standard form, it's always going to be a liquid in its standard form. And then like nitrogen, it's going to be a diatomic in its standard form, it'll be a gas. And carbon dioxide in its standard form would be a gas. So those are the kinds of things that we want to think about when we're thinking about the standard forms of things. So one other thing that's really important is to notice the balanced chemical equation. We're trying to just form 1 mole of methanol in this particular balanced chemical equation. So we want this to be a 1. We don't want to have to balance it to make this anything but 1 mole. So this side needs to be balanced. These can be different coefficients here, but we just want to form 1 mole of methanol. So we have to balance these on this side here, on the reactant side, so that we're only forming 1 mole on the other side, which is why we have to put a half in front of the O2. All right, so enthalpies of formation. The enthalpy of formation for the most stable form of any element is always going to be 0. There are a couple of exceptions to that. There are going to be some things that are bonded to themselves that have an enthalpy of formation of 0 all the time. Okay, so those are the ones that are listed here. We also have things like calcium, silver, sodium that are going to always have an enthalpy of formation that's 0 when it's bonded to itself. These are always the standard values. Some things can also exist, like hydrogen gas can exist without being bonded to itself, without being a diatomic. So we can have gas like this. We could also have oxygen gas like that without being a diatomic. We can also have nitrogen gas without being a diatomic, but these are not the most stable in their standard form. So these are not going to be enthalpies of formation of 0 because they're not the most stable. And also O3, it can exist under standard conditions as a gas, but it is not as stable as O2. It is not the most stable. This is much more stable, so that's going to have an enthalpy of formation of 0. The same thing can be said with carbon. Carbon is going to have a solid form when it is in its standard with 25 degrees Celsius and 1 atmosphere. but it has two different geometries, graphite or diamonds. Graphite is actually more stable under standard conditions, so it is going to have an enthalpy of formation of 0, where diamond is actually going to have an enthalpy of formation of 1.88 kilojoules per mole. So that is definitely something you just want to keep in the back of your mind. These are actually values they will be giving you in the problem. So it's not something that they'll be giving you this giant list, but they'll be giving you these values in the problem. So it's not something you'd even have to look up in this particular case. Okay, so the formula for calculating this is not going to be given to you on your formula sheet. This is something you just need to know, that it's the sum of the products minus the sum of the reactants, and you need to make sure that you have that stoichiometric mole there, the coefficient. Also, another thing you want to do is when you have the reactants, you want to change the value of the formation, the enthalpy of formation, to a negative, because you're not forming the reactants in the reaction. You're actually releasing them. You're breaking these bonds, so you need to change the sign. They'll have the same magnitude, but you need to change the sign to a negative because you are actually breaking apart these reactants. So the heat of formation is going to be the opposite charge than what you have in your appendix, whatever it is that you're looking at. So the overall equation is going to be the products minus the reactants. Right, I have most of the rest of these slides are going to be on the pear deck, but this is just one little quick thing I want to tell you. This right here is just something you might see on a list. This could give you the actual enthalpies of formation of some different things. This is just giving you a time frame of when they were discovered. Can't erase my pen. So just kind of an FYI if you'd like to know these. All right, another short video, and I will see you guys